Welcome. So in today's explainer, we're totally unlocking the secret codes of math. We're going to take those concepts you might have vaguely heard about in a classroom and reveal them for what they really are, the hidden architecture of numbers. If you've ever felt like math is just, a bunch of random rules, well, get ready, because we're going to make it all click right now.
All right, let's kick things off with a super quick math checkup. No pen, no paper, just your brain. I'm going to give you a 3-second mental challenge. Ready? Is 1 a prime number? 3, 2, 1. Okay, if you instinctively said yes, I definitely need you to stick with me, because by the end of this explainer, you're going to know exactly why 1 is literally in a league completely of its own, and I promise you will never forget it.
To understand why, we really need to look at what we're actually dealing with today. We're talking about the invisible DNA of every whole number, multiples and factors. Seriously, I want you to stop thinking of these as just boring vocabulary words to memorize for some test. They absolutely aren't. They're the underlying genetic code that cracks algebra, simplifies fractions, and honestly, makes complex equations an absolute breeze.
So, let's jump right into part 1, factors, or as I like to call them, the ingredients of a number.
A factor is really just a whole number that divides into another number exactly, leaving 0 leftovers, no decimals, just clean division. I kind of like to think of it this way. If a number were a baked cake, the factors would be the original ingredients that went into making it. And there's this beautiful symmetry to this, because factors always travel in pairs. As you'll see here, this brilliantly illustrates exactly what I mean. Let's hunt down the factors of 24, systematically. We start at 1. 24 divided by 1 is 24, so our first pair is 1 and 24. Then, 24 divided by 2 is 12, giving us 2 and 12. We keep going, 3 and 8, 4 and 6. But when we hit 5, well, it doesn't divide cleanly. We get 4.8, so we just skip it. The next number is 6, but look closely. 6 is already on our board from the 4 and 6 pair. The second a factor repeats, boom, you've hit the mirror line. You can stop digging because you found every single factor. It's just perfectly symmetrical.
Which brings us back to our primetime question, why exactly isn't 1 prime?
To answer that, it all comes down to the strict definition of what makes a number prime or composite. A prime number has exactly 2 distinct factors, 1 and itself. Take the number 17, for instance. The only way to cleanly make 17 is 1 times 17, exactly 2 factors. On the flip side, a composite number, like the 24 we just looked at, has more than 2 factors. We literally found 8 different ingredients for 24, so it's definitely composite.
And this leads us right back to the unique case of the number 1. I mean, what are the factors of 1? Well, it's just 1. That is exactly 1 factor, not 2. Because 1 only has itself as a factor, it basically sits in its own special category. It's neither prime nor composite. It is the fundamental starting block. Think of it as the number that builds everything else in the universe but isn't built from anything smaller. Pretty cool, right?
All right, moving on to part 2, prime factorization, which is basically smashing numbers down to their atoms.
You see, every single composite number out there is just a bunch of prime numbers hiding in a trench coat. Any composite number can be smashed down until it's nothing but prime numbers multiplied together. Let's use our absolute weapon of choice, the factor tree, to smash the number 72 down to its raw atomic structure. Step 1, start with 72 and pick literally any factor pair. Let's use 8 times 9. Step 2, neither 8 nor 9 are prime, right? So we break them down further. 8 becomes 2 times 4, and 9 becomes 3 times 3. Now 2 and 3 are prime, but that 4 is still composite. So, step 3, we smash that 4 into 2 times 2. Step 4, we gather up every single prime number left dangling at the ends of our branches. That's 3 2s and 2 3s. Finally, step 5, we write this out elegantly using powers. 2 to the power of 3 times 3 to the power of 2, and there you have it, the atomic structure of 72. Nothing but pure prime building blocks.
Now, I really want you to notice the golden link here between factors and multiples. If factors are the ingredients going into a number, multiples are the products coming out. They're really just 2 ways of describing the exact same mathematical relationship. If 3 is a factor of 12, then 12 is naturally a multiple of 3. It's honestly just like a parent and child relationship. It's the exact same family tie, you're just looking at it from a completely different direction.
And a multiple is simply what you get when you multiply a number by any whole number. That means finding multiples is basically just playing out your times tables. The first 5 multiples of 7, just count them up. 7 times 1 is 7, then 14, 21, 28, and 35. Super simple, right? But trust me, it becomes incredibly powerful when we start comparing numbers.
So let's compare some numbers in Part 4, the highest common factor, or HCF.
When we compare two different numbers, the highest common factor is the absolute biggest factor that they both share. Think of it as finding the largest possible overlap in their ingredient lists. Now, we have two ways to do this. For smaller numbers, method 1 is perfectly fine. Just list out the factors. Look at 18 and 24. We list their factors and can clearly see that 6 is the highest number on both lists. Easy enough. But for massive numbers, you're going to need method 2, which I call the big number destroyer. You basically prime smash each number into its atomic structure. Take 48 and 60. You find their common primes, which are 2 and 3. Then, to pinpoint the overlap, you just take the lowest power of each common prime. The lowest power of 2 between them is 2 squared, and for 3, it's 3 to the power of 1. Multiply those together, so 4 times 3, and you get an HCF of 12. That's literally the highest common ground they share.
Now let's flip the script in Part 5, the lowest common multiple.
If the HCF is all about what goes into the numbers, the LCM is about what the numbers go into. It is the smallest number that both of our original numbers can divide into cleanly. In other words, it's the very first number that pops up in both of their times tables. To find the LCM using our precision prime tool, we actually flip the HCF rule completely upside down. Let's look at 48 and 60 again. Step 1, identify their prime structures. Step 2, instead of taking the lowest power of common primes, we take the highest power of every prime that appears anywhere in either number. So we grab 2 to the power of 4, 3 to the power of 1, and 5 to the power of 1. Step 3, just multiply them all together. 16 times 3 times 5 equals 240. And there's your lowest common multiple.
Okay, this next part? This brings us to a mind-bending piece of mathematical elegance. The magic formula that links the whole shebang together. For literally any two numbers, let's just call them A and B, if you multiply them together, it will always equal their highest common factor multiplied by their lowest common multiple. This is basically your instant verification tool for any two numbers you ever work with.
Let's actually test it just to be sure. If you multiply our original two numbers, 48 and 60, you get 2880. Now, if you take the HCF we found, which was 12, and multiply it by the LCM we found, which was 240, boom, you also get 2880. It perfectly balances out every single time. It's literally math verifying itself. No way, right? So here is your ultimate cheat sheet to lock all these concepts in. Keep these rules in your back pocket. Factors are ingredients that travel in pairs. Multiples are just your times tables extending outward. Prime numbers have exactly two factors, leaving the number 1 in a bizarre category completely by itself. You can smash any composite number down using factor trees. To find the HCF, take the lowest power of common primes. And for the LCM, take the highest power of all primes. This right here is the invisible math DNA we've uncovered today.
All right, I'm leaving you with a final challenge to test out your new skills. I want you to pause this explainer, grab a piece of paper, and find the HCF and LCM of 36 and 45 using Prime Factorisation. Seriously, put your atomic smashing skills to the test. Once you figure it out, you'll realize you aren't just doing arithmetic anymore. You're actually deciphering the underlying code of mathematics. And remember, once you truly understand the code, the numbers never lie. In fact, did you know that these exact same prime building blocks are what secure your credit card data and passwords on the internet every single day? But exactly how they manage to do that? Well, that's a mystery for our next explainer. Thanks for hanging out and keep learning.